Okay, maybe, yeah, in this tutorial, to start off, maybe we'll talk a little bit about the case of Sn plus and its representations, just very briefly about how one can kind of do similar, graphical calculus kind of things to sort of try and get a handle on the representation theory of that. So for Sn, so actually maybe going back to the lecture this morning, On plus. So of course we're interested in representations of On plus. And the representation theory of a group or a quantum group, this is a category. So this has objects, which are, let's say, unitary finite dimensional representations. And its morphisms are intertwiners, so these spaces of linear maps. And in a way, sort of in graphical language, this category of representations, its data is really just specifying your intertwiners, right? And then the objects are going to be just basically tensor powers of your basic fundamental representation. And what we saw was that this is, and I'm going to use kind of vague terminology here because I haven't really talked about tensor categories at all, but it's reasonable to say something like this representation theory is generated by two maps, one object and two maps. The object is U, which is our fundamental representation. And morphisms. Well, there's always going to be one morphism, which is this through string going from U to U, and the cup, which is this R, from the trivial object going into U tensor U. Okay? So we have these two maps, this object, and the things we can do is take tensor products of U, and then acting on tensor products are the natural morphisms you can get from this sort of, these two maps. Okay? And what you get are temporally Lieb diagrams interpreted canonically as linear maps. Okay? Right, and so that's the setting of On plus, and from this we got, for example, the dimension of the endomorphism space of any tensor power, which then allows you to really understand how characters decompose, and they are basically Chebyshev polynomials in the character of the fundamental representation. And the way Chebyshev polynomials decompose when you multiply them tells you the fusion rules, and that's how you get these SU2 fusions. Okay? So what happens if you want to look now at Sn plus? Okay, we're going to assume that n is bigger than or equal to 4, so that this is truly a quantum group and not just Sn, so that we actually get something new. And the question here is, right, so we have now a different C-star algebra. So the C-star algebra Sn plus, this is generated by these Pij's such that the matrix capital P is a quantum permutation. Okay. And what does that mean? Remember, so P is a unitary matrix, and its entries are also self-adjoint projections. Okay, so rows and columns sum to 1, and get all that stuff. Okay, so in particular, I mean, P is an orthogonal matrix. Sn plus is going to be a quantum subgroup of ON plus, okay? So you would expect, you know, if you think about morphisms and what happens when you go to something smaller, the representations of Sn plus this is a category again, and it's generated by, well, one base object, P, which is an object. So this will be some category C. This is an object in C, right? And I can take tensor products with P. That'll get new objects. I can look at direct sums. I can look at sub-objects and so on. I can get a bunch of objects. But that's the thing that gives me everything through this sort of generation process. And the morphisms of this category are generated by, well, just as before, in the orthogonal case, we're going to have the identity map from P to P. And then there will be, because P is orthogonal, same calculation tells us that we have this map, R, once again. But there's going to have to be at least one other morphism which guarantees that the entries are self-adjoint projections. And we can make a few choices. A natural one would be this map, which I'll graphically draw as a tripod or a trivalent vertex. Okay. So what is this trivalent vertex? Well, this is a map from P to P, P tensor P into P. Okay, and of course P is living on Cn. This is a map from Cn tensor Cn into Cn. And it's the multiplication map view when we view Cn as a commutative algebra. Okay? So again, so again, I'm thinking of Cn just as a commutative n-dimensional C-star algebra and the usual multiplication. And the question is, why should this be a morphism? And the answer is coming from what Mateusz told us, I think, on the first day, which is that Sn plus is equal to the quantum automorphism group of this C-star algebra Cn. Okay? So the action of Sn plus on this C-star algebra is nothing other than the fundamental representation P. Okay? And being a multiplicative map is really actually expressed at the level of this category, is saying that the multiplication map on this representation space should intertwine the double tensor power of P with P. Okay, so that's sort of the at least heuristic reason, and you can literally just check that if you have these three things, you can again play the same game, try and generate all possible maps that you get, and you're going to get some new spaces of linear maps which are defined combinatorially in terms of these pictures. And in the end, what you're going to get is something like, so end of P tensor K. So this is the endomorphism algebra. So these are the invariants of Sn plus acting on P tensor K. So this is C to the n tensor K. This is it's a temporally Lieb-like thing. It's the linear span of some diagrams d pi, now a non-crossing partition, not necessarily a pairing on 2K points. Okay, so again, picture of one of these d pi's is going to be something like this. So example, let's say k is 3, maybe 4. Okay, so again, I'm going to have 4 points here, 4 points here, and I can now see what sort of operations I can do. For example, if I was to compose this tripod with the cup, this would create a loop, and there's going to be some sort of combinatorial rule which tells me this loop can basically be contracted, maybe with a scalar, and then this will just give me a singleton block which corresponds to this thing up here. Okay, so you're going to have sort of pictures of this form, something like this. This would be a partition of 2 times 4 points, a partition of 8 points, where this is a singleton block, this is a 3 block, this is a 2 block, and that's a 2 block. So you get some more diagrams than just temporally lead, right? Temporally lead diagrams are going to be a particular instance of these types of things, but you're going to get more in general. Okay, and so once you know this and prove it, and of course it's not, it's non-trivial to see that sort of the abstract diagrammatic algebra you get from these things is actually giving you exactly this. But once you know that, one can go and you can get a conclusion, which is Sn plus for all n bigger than or equal to 4 has SO3 fusion rules. Okay, so i.e. We have a complete set of irreducibles given by, let's call them VKs, k bigger than or equal to 0. V0 is the trivial representation. V1 is P direct minus the trivial representation. So P in the case of a quantum permutation group is not irreducible because the columns sum to 1, which means the all ones vector in Cn is going to be an invariant vector. So you're going to have at least one copy, which then you can remove, and the rest will be actually irreducible. That's what that is. All right, and then the rest are given by a similar raising and lowering type thing. If I take V1 and I tensor it with VR, this is actually equal to VR plus 1, direct sum up to equivalent VR, direct sum VR minus 1. So those are the fusion rules that the group SO3 has. So again, this is quite striking when you see it for the first time. You have the ordinary groups Sn. Their representation theory is very complicated, right? There's a lot of people who spend every day of their lives thinking about Young diagrams and Tableau and stuff like this. But for these quantizations, somehow the non-commutativity prohibits there being lots of intertwiners for these representations. So again, intertwiners are really telling you about algebraic relations, and when you make things more free, there's fewer algebraic relations, which means these morphism spaces tend to be smaller, which makes the representation theory more rigid. Right, so that's sort of the idea there. And now maybe I want to spend just a few more minutes talking about or commenting on some things that Ivan said regarding quantum isomorphisms of graphs. Okay, so let's suppose G and H, these are graphs on, let's say, n vertices. So Mateusz told us that the quantum automorphism group of, let's say, G, this is described at the level of C-star algebras in terms of really asking that it is the quantum permutation group. So you want to quantum permute vertices of a graph in a way that preserves the edge structure. So first thing you have to do is quantum permute vertices, and then you want to add a requirement, namely a relation which ensures that you respect the graph structure. And as Mateusz wrote it, it's exactly asking, let's say, P again is my fundamental matrix, is asking that basically PAG equals AGP. Okay? I.e., you go back over here, if you think about it in the representation theory language, it's saying we want to take the representation category of Sn plus, which has all of these things, and add something else, right? We want to add P, or sorry, AG. Okay? So i.e., at the level of representation categories, the representation theory of aught plus of G is going to be, right, maybe I'll, because I have, all right, just because I used G for group before, so maybe I'll just do this. Okay. So the representation theory of this quantum group is going to be generated by a string, a cup, a tripod, and also some new string diagram, which I'll write as AG, like this. Right, so you're just adding a new relation, and the new relation is really at the level of representation theory. You're adding an intertwiner. Okay? And what happens is when you throw in an intertwiner, you start with something non-trivial. If you were to randomly select an intertwiner, throw it in there, the category you're probably going to get is pretty small, or big actually. It'll be, you know, if, for example, if AG has lots of eigenvalues, then the spectral subspaces will be invariant, and then this could actually end up giving you all finite dimensional Hilbert spaces. And then, of course, well, that means your quantum automorphism group is trivial. So that's what this is. All right. So I want to now just say something about how this relates to quantum information theory. So we had something like this, right? So two graphs are quantum isomorphic if and only if, and this is this result due to Laura and David and co-authors, many co-authors, Atsarius, I think, and Barbatsiotis and Severini, maybe, Zamal, I don't know, a bunch of people. But yeah, so I'll say, yeah. This is actually equivalent to an algebraic condition saying that there exists a quantum permutation, P, okay, where now I think of like the I vertices corresponding to vertices of one graph and the J's is for the other graph. A quantum permutation, these two graphs are size n, and the condition is that AG, let's say AGP is equal to PAH. So, yeah, so this is clearly very related to the setting of what we've been looking at, right? So you see there's actually a kind of a combination of two ideas. So P is going to be, so this is now just living in some B of H, like, so this will be an Mn of B of H, right? For some Hilbert space. So P is going to correspond to a representation, but actually a representation in the usual sense, not quantum group sense. This is going to be a star representation of, well, C of Sn plus for sure. u of Sn plus. Okay. But it's sort of at the same time behaving like some sort of representation.
I can make some good reading letters, but I think the subscripts of A are the same on both sides.
Oh, yeah, yeah, sorry. Let's say, yeah, AG.
So, yeah.
This letter, just out of curiosity.
It's a funny G. Funny G, yeah. A Canadian G, yeah. Yeah, it's a Canadian G. A Canadographic G. It's a new symbol I'm gonna make up. Okay, so it's also behaving like some sort of representation of a quantum group, but it's not symmetric anymore, right? You have H and G, the adjacency matrices. So so actually, it's like, you should think of it as kind of like it's sort of like a unitary representation of some sort of, and this is very vague, space of, quantum isomorphisms from, let's say, G to H. Right. And one can make sense of this. I mean, you can look at the relations, right? We have a magic unitary, and we ask that its coefficients form, have all the relations of a magic unitary, and then we have this commutation relation. You can actually define a universal C-star algebra with those relations. You get kind of like a generalization of a quantum automorphism group. It's now a quantum isomorphism space between the two graphs, right? And essentially, the operational interpretation of quantum isomorphism graphs is saying that this quantum space of isomorphisms is non-trivial, right? So it has some representation on an Hilbert space. So a lot of activity by many people, I'd say most notably here, is due to Laura and David and his group as well in the Technical University of Denmark, on sort of looking at sort of quantum isomorphisms and understanding these in terms of representation theory, unitary representation theory of quantum groups. So let me just, I want to comment a little bit on this. So we can consider the representation theory of the automorphism group of one graph. Okay, this is generated by, again, this through string, this cup, this trivalent vertex, and then A sub G. Okay. And similarly for the other one, it's generated by actually, if we identify the spaces of vertices, the exact same maps, except this one changes to the other thing. Right? And if G is quantum isomorphic to H, this means that P exists, such that AG P is equal to P A H for some Hilbert space. All right, and then you can sort of in a natural way do what you do when you compute representation theory. You can look at tensor powers of this P, even though it has this asymmetric condition. So I can form this sort of the natural analog of P tensor K. And suppose I take a morphism from, and this is going to be a morphism of the quantum automorphism group of G from, yeah, P tensor K into some P tensor L. Now this is, of course, the actual morphism space, okay? So I'll say, yeah, U tensor K, U tensor L, where U is the fundamental representation of this quantum group. And if you play around with this a little bit, this P here, which is this asymmetric version of a representation, commutes all of these maps, but it turns this one into an AG if it's an AH. So you move it over. So P tensor K of T is going to be equal to something, if I move it to the other side, if I just think of it as like a monomial, maybe a tensor monomial in one of these things, right? What it will do, so I guess if I want to make this right, this should be an H here. T will be brought over to the other side. It'll turn into something over here. This will be P tensor L. What do I want to say here? Yeah, I think that's right. So there will exist some S morphism of the other quantum group of G now, canonigraphic G, okay, such that this equation holds. And okay, it's not an immediately clear thing, but it's true that the map, you get maps basically, phi from the morphisms of aught plus of G into the morphisms, or maybe the other way around, H to G of aught plus of G via phi of T is whatever S you get on this side. Okay. And these maps here are actually nice. They are they respect tensor products. They respect the involution structure. If you're looking at an actual endomorphism algebra here and here, you will get a C-star algebra isomorphism of endomorphism algebras. Okay, so in other words, the representation categories of the two quantum groups are the same, and I'll say this in quotations, because I'm being a little bit vague here about same. What this means is that the two things are, so this phi will induce sort of an equivalence of categories. Okay, so this is monoidal equivalence. So in other words, I mean, sort of the upshot of thinking about things this way is that the existence of P implies something that is like combinatorial linear algebraic in nature, okay? Which may be extremely hard to verify, and is actually provably extremely hard to verify in many examples. What you get actually is that you can go the other way. So if you happen to have two graphs whose representation categories are naturally kind of the same via some natural systems of isomorphisms, there's something called essentially a Tanaka-Krein reconstruction theory, which allows you to go the other way. So Tanaka-Krein theory says that you can go the other way. So again, I'm going to be very vague here, but basically if these representation categories are the same. Now, here when I mean the same, I mean not just equivalent in the sense of the right categorical notion. I mean also the same in a very strong sense, namely the first three maps, the cup, the through string, and the tripod, are like mapped to the same thing. And it's only the adjacency matrix that changes in terms of generators. Then you can actually prove the existence of a Hilbert space and a magic unitary or quantum permutation. Okay? Then there exists a P such that you know, A GP is equal to PAH. Okay? So these are kind of equivalent things, which is of course saying the graphs are quantum commuting isomorphic. Okay? And I think it's worth mentioning that this sort of equivalence here actually has a very nice graph theoretic interpretation due to David and Laura, which is that you can essentially measure this equivalence in terms of counting homomorphisms from planar graphs into G and into H, and if they agree for all planar graphs, these things are the same. So, pardon me? It's just, yeah, that's the point. It's that condition guarantees a unitary fiber functor, which, yeah.
It's important that some of the quantum automorphism groups, they don't have to be isomorphic as well. This is a weaker notion of P1.
Yeah. So this is very, you know, like a very striking result, and it sort of it's very interesting because it gives like a purely combinatorial graph theoretic interpretation of something that is very, you know, from the quantum information theory side, coming from something that's quite operational. You might ask, okay, this is great. You can turn all of this quantum isomorphism, which is originally coming from non-local games, into some equivalent statements about representation categories. And I did want to mention that actually, this thinking about it this way actually gives new examples of quantum isomorphic graphs. So there is some really nice work due to Ada Chan and I think it's named Robert Martin, and also independently due to Daniel Gromada, where they looked at real Hadamard matrices. And one can associate a graph to a Hadamard matrix, and you can ask when are two Hadamard graphs isomorphic or not isomorphic if they have the same number of vertices, let's assume. And it turns out that you have many different non-isomorphic Hadamard graphs, but when you think of them in terms of quantum isomorphic, the quantum isomorphism of Hadamard graphs only depends on the size of the vertex set. And the way this is shown is that, well, you look at these two things and show that the associated categories of representations are the same. The only invariant is the number of vertices you start with, which is kind of a striking thing because it's an instance where we know that there's some quantum isomorphism, but we have no idea about the kind of resource that is used to implement this. And I think this is kind of a fascinating question that is really, I think, at the heart of maybe what this program is about. Really, we get something from quantum groups towards quantum information and operator algebras and quantum information, and also it's going the other way, and that it's inspiring kind of people to think about different kinds of quantum groups. And so, yeah, I think that's pretty much all I wanted to say. I don't know if Mateusz, you wanted to. Okay. Yeah.
So, if the existence of a quantum isomorphism does not guarantee that the quantum automorphism groups are isomorphic. Is the quantum groups being automorphism groups being isomorphic still a weaker notion than the graphs being classically isomorphic?
Yes, I think in general you would expect that. Sorry? Oh yeah, that's true. Yeah, yeah.
Is the space of one isomorphism like allow?
Yeah, it's yeah. And maybe just a small comment. If you were to ask, you start with an ordinary graph, let's say G, and you ask for another sort of representation category that's equivalent to your one. But you ask, you don't ask that the sort of the cup and the tripod and the through string will always be the identity. But the cup and the tripod, if you ask them, you allow them to be mapped to something different, you don't get a graph. You don't get the automorphism group of a graph anymore. You get the quantum automorphism group of a quantum graph. So quantum graphs naturally arise this way by looking at fiber functors on, for example, classical quantum automorphism groups of graphs. So in that sense, they arise as well.
Any other question?
I have maybe a comment that ties this neatly back to the quantum information theory lecture.
Yeah.
So you mentioned this result by David and Laura that quantum isomorphism is equivalent to this having the same number of homomorphisms from planar graphs.
Yes.
The original proofs use the theory you just outlined.
Yeah.
But I want to just say that my co-authors recently, or actually I wasn't on this, my colleagues I should say, they recently gave another proof of that.
Oh, cool.
Using the NPA hierarchy.
Ah, very nice. Yes, I had heard about this, but I had not seen it. Yeah, that's cool.
So somehow this all ties all the topics neatly together.
Is this on the archive now? Okay, good.
So then let us thank all the speakers of this quantum. I would like to thank the organizers for this wonderful workshop. Mixed